In Chapter 7, we start looking at different types of chemical bonds, and in particular, we're going to be looking at two different types of chemical bonding. We then go on and see the importance of the role that the outermost electrons on an atom play in forming chemical bonds. These are electrons that are referred to as the valence electrons, and we develop some really simple systems for representing what the valence electrons are doing in different compounds using a system known as Lewis symbols. So that's really kind of the whole sort of gist of the chapter. It's quite a long chapter, and we'll be tackling it in 2 sections across 2 weeks. So first of all, we're going to characterize the different types of chemical bonds that we find present in compounds and elements. So the atoms of a compound are held together via chemical bonds, and compounds are generally classified according to the type of bonding that is present. So compounds can be classified as either molecular compounds, or sometimes referred to as covalent compounds, or ionic compounds. So these compounds have different characteristics. Molecular compounds can be either gases or liquids, or generally just low melting point solids, and they tend not to be very good conductors of electricity. Even if we melt them down, they still don't like to conduct electricity very well. Ionic compounds are quite different though. Ionic compounds are all solids at room temperature, and they tend to have very, very high melting points. If we melt them or we dissolve them in water, ionic compounds are very good conductors of electricity, which is telling us something about their structure. It's telling us about the fact that they are made up of positive and negatively charged particles, and that when we melt the ionic substance or when we dissolve it in water, that those positive and negative particles can move around. But when they're in the solid state, those positive and negative particles are unable to move, which is kind of interesting. Now, the other interesting thing about ionic compounds is that they don't exist as molecules, but rather they exist as a network, or what we might say an array, of positive and negatively charged particles. We refer to these as ions. So ionic compounds in the solid state are crystals of an approximately infinite array or indefinite array of positive ions and negative ions. And so there's no discrete sort of molecules in these guys. They just have this approximate infinite lattice of particles. So the type of bonding that we find in ionic compounds is called ionic bonding, and this is formed through the transfer of electrons. And again, remember, the electrons that are going to be transferred that are involved in bonding are those that are on the outer edge of the atom. In molecular compounds, the type of bonding that's present is are covalent bonds, or also referred to as molecular bonds. And these are bonds that are formed through the sharing of electrons. So we have 2 different ways in which chemical bonds are formed: transferring electrons and sharing electrons. So chemical bonds result from the interaction of electrons on different atoms. The electrons that are going to be forming these chemical bonds are called the valence electrons. So what are valence electrons? Valence electrons, we already kind of touched on this idea. They are those that are in the outer S and P subshells, and then we say any partly filled D subshell. So that's only going to be relevant for the transition elements. Okay. The other thing to think about when we're talking about chemical bonds forming is to recognize that some arrangements of electrons are very stable. That is, they don't like to change in comparison to other arrangements of electrons. So what ones make up the valence electrons? We already talked about that. These are the ones that are in the outer S and P subshells. They're the ones that are on the outer surface of an atom. Okay. So the attractive force that holds 2 atoms together is called a chemical bond, and chemical bonds result from either transferring electrons, that's called ionic bonding, or sharing electrons, that's referred to as covalent or molecular bonding. atoms interact with one another through their valence electrons. These are the electrons that are going to be involved in the formation of chemical bonds. So let's focus in on these valence electrons, and as I promised, we're going to relate it to this concept called the Lewis symbol. So we define a valence electron of a representative element, that's an element that doesn't have, that isn't in the D block, or a noble gas, as being an electron in the outermost shell. For the representative elements, those in the groups that have an A in their designation, this is always going to be an electron that's in either an S or a P subshell. Now, there's an American chemist by the name of Gilbert N. Lewis, and he developed a really simple system for illustrating the number of valence and electrons an element has. And just remember that for the representative elements, the group number equals the number of valence electrons. Okay, and then that makes everything real simple. So what you do in the Lewis symbol for an element is you put one dot equal to the number of valence electrons around the atom symbol. So an element that's in group 4 would have 4 valence electrons. So we go 1, 2, 3, 4. Now, the important thing to recognize is it doesn't matter where you where you begin placing the dots, north, south, east, west, or whether you go clockwise or anti-clockwise. That's not important. What is important is you put one dot at each of the 4 compass points before you begin pairing up. Okay, so that would be an element with 5 valence electrons there. So that's it really, and then all you have to remember is that for a representative element, that's one that's in the A groups, the number of valence electrons is just equal to the group number. So everything in group 1A gets 1 dot, everything in group 2A, 2 dots, everything in group 3A, 3 dots, and so on. So the number of valence electrons about a representative element is conveniently illustrated using its Lewis symbol. The number of valence electrons a representative has is just equal to its group number. And keep in mind that there are only 8 A groups. So what that tells us is that the maximum number of valence electrons around a representative element is 8. So we now kind of know how many electrons an atom has to form all of its bonds. It's just equal to its group number. So something that kind of comes out from considering what atoms are the most stable and least likely to change their electron configuration is to think about what we call the octet rule. So the least likely to react elements of the periodic table are those that are in group 2A. And these are elements that either have 2 electrons in a completely filled 1s subshell or a completely filled S and P subshell in their outermost shell. So having this 8 electrons in your outermost shell is a very, very stable electron configuration. So what we conclude is that the most stable electron configuration is one in which the atom has a complete outer S and P subshell. Alright, so something that looks like that, where the N refers to the number of the highest shell. And what we find is that atoms that don't have that stable electron configuration, they're going to do everything they can to get it by forming chemical bonds. So atoms will tend to keep forming chemical bonds until they obtain a stable noble gas-like configuration, and then they stop reacting because they're stable at that point. So this is summarized via what's called the octet rule, and it just says, in forming chemical compounds, atoms of elements tend to lose, gain, or share electrons so as to obtain a noble gas configuration. So losing and gaining they're the opposite of each other. They make up transferring electrons would be another way of saying that. And then sharing, that's you're forming your covalent or molecular bonds, isn't it? Transferring electrons, remember, is forming your ionic bonds. So atoms are either going to form ionic bonds or covalent bonds until they get a noble gas configuration, and then they become unreactive, and they will stop making new bonds. So the noble gases are the most stable elements, that is, they are the least likely to react. They all have a completely full outer S subshell or a completely full outer S and P subshell. The only one that just stops at an S subshell is helium. All of the others have an S and a P subshell. Atoms that don't have a stable octet, they acquire it by either sharing electrons, that is, forming covalent bonds, or transferring electrons, that is, forming ionic bonds. Once they do, they become unstable, and that's what we call the octet rule. Okay, so now we're going to apply the octet rule to see how it comes into play in the formation of ionic bonds. So it's important to realize that atoms have an equal number of protons and electrons. And so as a result, because protons are positive and electrons are negative, they have no overall charge. Now, if an atom loses or gains one or more electrons, it forms a charged species that we call an ion. In particular, when an atom loses one or more electrons, it forms a positively charged species that we call a cation. And you can remember this, cations are, because they're cats, positive. Okay, there we go. And what we get is, for every one electron lost, we get a 1 positive charge on our cation. If we lose 2 electrons, if our atom loses 2 electrons, then we get a 2 plus charge. You see? And if our atom loses 3 electrons, you can see that we get a 3 plus charge. Now, what are the atoms on the periodic table that like to lose electrons and form cations? They are hydrogen and the metals. They all love to lose electrons and form cations. Now, when an atom gains one or more electrons, it forms a negatively charged species that we call an anion. And what you have to recognize is that for every electron gained, we get a 1 negative charge. So if I take an oxygen atom and I add 2 electrons to it, I form an ion with a 2 negative charge. If I take a phosphorus atom and I add 3 electrons to it, I form an ion with a 3 negative charge. And the non-metals love to form anions. Okay, and you can remember anion, A negative ion. So you can say A negative, then we've got ion is an anion. It's not as much fun as positive cations. Okay, so this is a very important thing to recognize. Electron loss to form a cation and electron gain to form an anion occur simultaneously. We don't have free electrons floating around. So here's a metal, sodium, has 11 electrons. One of those electrons in its outermost shell. Here's a non-metal, chlorine. It has 17 electrons. Metals like to lose electrons. So sodium likes to lose 1 electron, transfers it over to chlorine because chlorine likes to gain electrons. And so what are we left with now? Well, now we're left with a single positively charged sodium ion that has 10 electrons. And then we have a single negatively charged chloride ion that has 18 electrons. Now, if you look at your periodic table, what has 10 electrons is neons, not argon at all, is neon. And what has 18 electrons is argon. Okay, so the sodium atom, by losing 1 electron, it gets the electron configuration of neon. The chlorine atom, by gaining 1 electron, it gets the electron configuration of argon. The only problem is now that the sodium has a positive charge and the chlorine has a negative charge, they're going to get stuck to one another. So everybody gets to obtain a noble gas configuration in this scenario. The only difficulty is they are now stuck together. So it is this attraction between the ions that form when we transfer electrons that gives us what we call the ionic bond. So ions form when atoms, or sometimes even actually groups of atoms, gain or lose electrons. When electrons are lost, we get cations. When electrons are gained, we get anions. The charge of an ion is indicated using a superscript following the atom symbol, and it indicates how many electrons have been lost or gained. When electrons are transferred from one atom to another, you'll get a cation and an anion forming, and they will stick to one another, and that's what we call an ionic bond. Okay, so one last section in this video is discussing the sign and magnitude of ionic charge. So what we mean here, the sign, there are only two options. It's either positive or negative, and magnitude is just another word for size. So the representative elements, they will lose or gain enough electrons to obtain the same number of electrons as the nearest noble gas. So we already just saw that sodium likes to lose one electron, so it's like neon. Chlorine likes to gain one electron, so it's like argon. Calcium likes to lose two electrons, so it's like argon. That gives it a charge of +2. And so on. That's how it kind of works. So how many electrons would aluminum like to lose? Aluminum has 13. It would like to be like neon. It loves to lose 3. So aluminum likes to form aluminum 3+. Bromine has 35 electrons. Bromine loves to gain 1 electron, so that it has the same number of electrons as krypton. Okay, so it's kind of, we can just have a look at this. Phosphorus loves to gain 3 electrons, so it ends up with the same number as argon. Oxygen loves to gain 2 electrons, so it ends up with the same number as neons. So if I want to work through here, the non-metals in group 7A love to form -2 ions. In group 6A, they love to form -2. In 7A, they like to form -1. In 6A, they like to form -2. In 5A, they love to form -3. The metals in group 1A love to form +1. The metals in group 2A love to form +2. The metals in group 3A love to form +3. So summarizing all of that, group 1A through 3A metals love to lose 1, 2, and 3 electrons when they form ions, forming +1, +2, and +3 ions respectively, whereas the non-metals in group 7A, 6A, and 5A love to gain 1, 2, and 3 electrons, forming -1, -2, and -3 ions respectively. Okay, a little bit of terminology. Isoelectric species are things that have the same number and configuration of electrons. So when we see an atom that has 10 electrons, we're going to say that it is isoelectronic with neon that also has 10 electrons. So here's an example of that here. The sodium atom there, 10 electrons. Neon, also 10 electrons. We would say that those two things are isoelectronic. So summarizing this, we can say that group 1A through 2A metals, they like to form ions that are isoelectronic with the noble gas that comes before them. For the nonmetals, group 5A through 7A nonmetals, they love to become isoelectronic with the following noble gas, that is the noble gas that comes after them. So here's fluorine minus, it has 10 electrons, that's going to be isoelectronic with neon that also has 10 electrons. Here's the sulfide anion, has 18 electrons, that is isoelectronic with argon, which has 18 electrons. Argon comes after sulfur, neon comes after fluorine. Okay, so we can predict the sign, positive or negative, and the size of the charge on an ion for a representative element. Namely, group 1A, 2A, and 3A metals, they form +1, +2, and +3 ions, whereas group 5A, 6A, and 7A non-metals, they form -3, -2, and -1 anions, respectively. There's a little bit of terminology in there. We say that two things are isoelectronic if they have the same number of electrons in the same configuration. Okay, so now we're just going to do this right now and get it done. In section 7.6, we look at how we can combine the Lewis structures of different atoms to indicate how an ionic compound forms. So, what happens when an ionic compound forms is that an electron lost by a metal and an electron gained by a non-metal occur concurrently, and we can indicate this process using Lewis symbols. So let's think about what happens when a lithium atom comes in contact with a chlorine atom. Lithium is in group 1A, so it has 1 dot in its Lewis symbol, and chlorine is in group 7A, so it has 7 dots in its Lewis symbol. Lithium in group 1A loves to lose 1 electron, which it transfers to the chlorine, which loves to gain 1 electron. Lithium's in group 1A, chlorine's in group 7A. So the lithium becomes singly positively charged, and the chlorine ends up with a full set of 8 electrons and becomes singly negative charged. These ions will then attract one another and become stuck together and form the compound lithium chloride. So we can use Lewis symbols to illustrate this transfer process. And that's a very common thing to be asked to do. And if you look in your book, I'll just find the page now. There are multiple examples in chapter 7 showing you how to do this. So let me just find it. If you look at examples 7.5 and 7.6, which are on, it's example 7.6, but the text that you want to read is pages 239 and 240. They explain very clearly how Lewis symbols are used to illustrate what is happening in the formation of an ionic bond. So when these ionic compounds form, what's important to recognize is that the metal will lose all of its outer electrons. They're completely gone, and the non-metal always completes this outer shell. So when you get to sort of after the transfer, your metal should have no dots around it, and your non-metal will have a full set of 8. By convention, we normally write the metal ion on the left as it appears in the periodic table, followed by the non-metal ion. Sometimes we have to do more than one atom in order to get the formula that we want. On Wednesday, I'll go through a bunch of examples of how we show how these things are drawn, so don't worry about that too much right now. Okay, just like that. So that's indicating that sometimes you have to put more than one of the ions there, because there you have to stack them on top of one another. Okay, we'll go through that at a later date. Alright, so Lewis structures can be drawn to show how ionic bonds form. So what we're showing there are the Lewis symbols of the individual atoms, and then we're showing how the electrons are transferred to form the ions. There's a little bit of convention there that we always draw the metal atoms and ions on the left, followed by the non-metals.